the nervous system's control of human leg external forces. My name is Pawel Kudzia. This is a collaborative work with Steve Bervinovich and Max Donlin at Simon Fraser University in Burnie, British Columbia. Humans are well adapted to move in many different ways and navigate many various environments. Consider a soccer player navigating the field, avoiding oncoming defenders. To score a goal, this player must execute motion precisely while adapting to the surroundings. Many might consider this a display of agility, that is, moving quickly and constantly redirecting their motion. Objectively, being agile correlates with excelling in other movement tasks such as running fast and jumping high. To excel in these tasks requires that people generate appropriate ground reaction forces that accelerate their center of mass. When the foot interacts with the ground, the external force vector has a magnitude and a point of origin. The magnitude component I refer to as force magnitude, and the point of origin I refer to as force position. The control of the magnitude of the force and of the position where the force is applied by the foot onto the ground are key determinants of translational and rotational acceleration. Effective control of these force properties may help explain human agility. It may help us understand the differences between other humans, between humans and other animals, and between humans and engineered robotic systems. The objectives of our research were therefore to characterize the performance of the human leg in controlling the force magnitude and force position of an externally applied force. Secondly, we wanted to compare the performance of people controlling leg external force to that of a robotic leg from an agile-legged robot. To accomplish our goal, we built a rig that constrained people vertically and horizontally over top of ground-embedded force plate. Participants stood in this rig on one leg in a posture that resembled the mid-stance of a run. On a screen in front of them, we provided them with real-time feedback of the force magnitude or force position signal that they were exerting onto the ground. Using step functions, we asked them to best match their real-time signal to the prescribed force magnitude or force position step function. They achieve this by pushing more or less, or by selectively shifting the pressure beneath their foot. Here's a picture of someone standing in our apparatus. To further describe the step response characteristics of leg external force control, we modeled the system dynamics and used system identification to estimate the unknown parameters. We use a second-order linear differential equation where Kp is the process gain describing the change in output y, induced by a change in input x. Z is the damping constant, T1 is the rate of change, and Td is the process delay time or dead time. To find these unknown parameters, we use numerical optimization, fitting the least squares difference between the model predicted and empirical data. Some of our experimental outcomes of interest, specifically for the control characteristics, were rise time, which is the time it takes for the signal to go from 10 to 90% of the target value, overshoot, which is the percent overshot above the target, steady state error and variability, that is steady state error and variability during steady state, and fall time, which is the time it takes to go from 90% to 10% of the signal value. We also evaluate the system bandwidth, and this is a measure of how fast the system responds to changes in the input command. Our study consisted of 2 experimental testing sessions, one for force magnitude control and one for force position control. We recruited 14 participants for our study. On the x-axis here is time, and for force magnitude control, y is magnitude in times body weight, and in force position control, y is displacement in centimeters. So participants performed 4 different step force magnitudes, as indicated by the dashed lines, and 4 anterior, posterior, and medial lateral step functions, as indicated by the dashed lines. These steps were evaluated in a randomized order, and participants were provided with sufficient training prior to the experiment. In both testing sessions, participants performed many repeats of each step magnitude while best matching the prescribed step function. When evaluating the performance, we use the 5 fastest responses, which will be considered their best performance. So moving on to some of the results. With force magnitude control, people were well able to match the prescribed step functions for both force magnitude control and force position control. In fact, the control performance for both force magnitude and force position control were quite similar. So here, the darker line is the mean, and the shaded line is each participant's average response for each of the evaluated 4 different size step targets. For force magnitude control, anterior posterior force position control, and medial lateral force position control. So we observed similar control performance in terms of speed and accuracy for both force magnitude and position control for all target step sizes. So here are some selective representative data. You can see the participants overshoot around 19%, have a rise time of around 200 milliseconds, a bandwidth of around 1.8, 1.6 hertz, steady state error, steady state variability, and fall times. And this is for force magnitude control at 0.45 times body weight, and force position control at 2.5 centimeters anterior, and force position control at 1 centimeter lateral. But regardless of the step functions, the results were quite similar for all. Next, moving on to the modeling, we found that a second order model was a good predictor of lag external force control. Best fitted R-squared values for all target step sizes and for both magnitude and position control were all above 0.85 R-squared. And this controller, and by extension the human leg, rises to step changes in 165 milliseconds and overshoots the target in 15 seconds. It settles on targets in 170 milliseconds and then exhibits no steady state error or variability. It can accurately track changes of force magnitude or position that oscillate twice per second, aka has a bandwidth of 2 hertz. We compared these human results to the MIT Cheetah, which is considered by some as the most agile-legged robot. And we got this data from Wensing 2017, and we found that the MIT Cheetah leg force control was 50 times faster and had nearly no steady state error or steady state variability for a similar type of experiment. So the control of leg force in the MIT Cheetah greatly exceeds the measured human performance. And our findings do not seem to suggest that the superior agility of humans is due to greater leg force control. So some takeaways. With our experimental apparatus that we developed, we found that participants were well able to control external force vectors. A second order model well describes leg external force control behavior in people. Our preliminary results suggest that robotic leg control is more accurate and much faster than human legs. And perhaps the superior agility of humans is not explained by enhanced leg force control. So our work here provides the groundwork in characterizing the control of leg external forces in young healthy humans. This approach could be used as a benchmark for comparing and developing future agile-legged robots. And future work may focus on understanding the effects of age, disease, fatigue, training, and injury on leg external force control and human agility in general. Thank you for listening, and I look forward to any questions you have and talking more about my project. My name is Pawel Kudzia, and you can contact me at pkudzia@sfu.ca or check me out on Twitter at pkudzia_biomech. Thank you.